Have you ever stopped to think about the invisible forces that are literally holding our world together? I mean, the forces that dictate how atoms bond and how our technology works? Well, today, we are diving deep into one of the most powerful forces in the universe, the electric force. Let's get into it.
So here's our game plan. We're going to start with a super simple rule you probably already know. Then we'll see how physicists actually measure it with crazy precision. After that, we'll put the electric force head-to-head with gravity, tackle a really weird problem about empty space, and uncover the brilliant solution. We'll even look at how some animals have literally evolved to use this force to survive.
All right, let's start at square one. I'm talking about the most fundamental principle that runs every single electrical interaction, from a spark of static to the firing of neurons in your brain.
It's that simple rule you learned back in school, and for good reason. It's everything. If you have two charges that are the same, say two positives or two negatives, they push each other away, they repel. But if you have two opposite charges, a positive and a negative, they pull toward each other, they attract. This basic push and pull, well, it's the foundation for everything we're about to talk about.
But, in physics, just saying attract or repel doesn't really cut it. We need to know how strongly they're pushing or pulling. And that brings us to the law that lets us put a number on this invisible force.
Okay, so this is Coulomb's law. Now, don't let the equation scare you. The idea behind it is actually pretty simple. The force, that's the F, really just depends on two big things: how much charge the particles have, the Q's, and how far apart they are, that's the R. The more charge you have, the stronger the force. But look at that R squared on the bottom. That's the really interesting part. It means as the distance gets bigger, the force gets weaker, and it gets weaker fast. This is what's known as the famous inverse square law.
So how did Charles Coulomb even figure this out, way back in 1785? Well, he used this incredibly delicate gadget called a torsion valence to measure these tiny, tiny forces. And he noticed something amazing. When he doubled the distance between two charges, the force didn't just get cut in half, it dropped all the way down to 1/4 of what it was. That was the inverse square law, right there in his lab. And just like the math says, if he cut a charge in half, the force also got cut in half. Pretty brilliant piece of detective work, really.
All right, so we've got this seriously powerful force, but how does it stack up against the one we feel every single second of every day, gravity? You might assume gravity is the heavyweight champion of the universe, but let's take a closer look.
Right off the bat, there's a huge difference between them. The electric force is all about charge, and it's got two moves. It can pull things together, or it can push them apart. Gravity, though, it's all about mass, and it only knows one move, attract. Gravity's always a pull, you never see it push anything away.
And that brings us to the main event. When we zoom way, way down into the world of atoms and molecules, which force is the real boss? The one that holds galaxies together, or the one that makes your hair stand on end?
The answer is just staggering. I mean, it's not even a contest. The electric force between two tiny alpha particles is 3.1 times 10 to the 35th power stronger than the gravitational force between them. That's a 31 followed by 34 zeros. It is an absurdly, incomprehensibly huge number.
And that right there is the key takeaway. On the scale of atoms and molecules, gravity is, well, it's basically a rounding error. It's completely insignificant. The reason you don't fall through the floor right now isn't gravity. It's the electric force pushing the atoms in your feet away from the atoms in the floor. All of chemistry, all of biology, it's all run by the electric force.
But this incredible strength created a massive conceptual problem for early physicists. It wasn't just that the force was so strong, it was how it seemed to work that just felt wrong, almost like magic.
And this was the heart of the mystery. They called it action at a distance. You could have two charges sitting in a perfect vacuum, literally nothing between them, and yet somehow they would exert this unbelievable force on each other.
So this led to a really deep question. How? How does one little particle send a message across a total void to tell another particle to move? It felt spooky. It was a puzzle that needed a much better, much more elegant solution.
And that elegant solution, it's one of the most beautiful and powerful ideas in all of physics. It's the concept of the electric field.
The big idea was to completely get rid of action at a distance. Physicists proposed that, wait a minute, maybe the charges don't interact directly at all. Maybe, instead, a charge changes the space around it. It fills the space with this invisible influence, and we call that influence the electric field. The field acts like a go-between, a messenger for the force. Think of it as a two-step process. Okay, step one,
You've got your source charge. Let's call it Q. It just sits there, and by its very presence, it warps or alters the fabric of the space all around it, creating this electric field that radiates outward in all directions.
Now for step 2. You bring another charge, a little test charge, and you place it somewhere in that field. It immediately feels a force. But here is the brilliant insight. The force is not coming from the original charge way over there. No, the force is being applied locally by the field itself at the exact point in space where the test charge is. The field is what does the actual pushing or pulling.
Now, if this whole field idea still sounds a little abstract, well, you're actually way more familiar with it than you think, because it's a perfect parallel to gravity. A big object, like the Earth, has mass, and it creates a gravitational field, G. Any other object with mass feels a force when it's in that field. It's the exact same logic. The electric field is to charge what the gravitational field is to mass.
And this whole concept of fields isn't just something we draw in textbooks. Nature itself figured this out millions of years ago, and some animals have evolved this unbelievable ability to actually sense these fields to hunt and survive.
So meet one of the planet's ultimate electric detectors, the shark. For a shark, the electric field is as real and as useful as sight, smell, or sound. It's another sense.
So how in the world does this work? Well, every time a fish moves, even just a tiny muscle twitch, it generates a very faint electric field. Sharks can pick up on these signals using a network of special, jelly-filled pores all over their snouts. Their sensitivity is off the charts. They can detect fields as weak as 5 times nanovolts per centimeter. This basically gives them an electric sixth sense, letting them see a flounder completely buried under the sand, just by detecting its heartbeat. It's a stunning, real-world example of the electric field in action.
And all of this brings us to one final, fascinating puzzle. If the electric force is so mind-bogglingly stronger than gravity at the small scale, why is gravity clearly the boss on the large scale? Why are planets and stars and entire galaxies held together by gravity, the weaker force? It's a great question that points to another deep truth about electricity, and it's the perfect place to leave things for today.